absolute extrema occurs when you have a graph over an interval that does maybe something like that. So we know we can identify a relative max, right? We can identify a relative min. Or is that a relative max or a relative min? Well, this right here is actually, I'm going to make this picture even better. Instead of stopping there, I'm going to give myself some more room. There we go. So much better. So is that really a relative max? Is that really a relative min? Because now I've got this over here that happens to be higher, right? If I measure this, this is up here, and the relative max is down there. So yeah, that pink one is a relative max. This would be considered an absolute max. Okay, so that would be over the entire graph from beginning to end. That's an absolute max. Now, what is this right here? Well, this would have been a low point. Right here, this is a low point. Well, this is a relative min because it's not the absolute lowest point. So it's not an absolute min. It's a minimum, though, because it's lower than the points that come after it, which makes this not a relative minimum, but when you look at the graph as a whole, this happens to be the absolute min. So absolute means the absolute lowest point. Relative means it's a low point, but it's not the lowest point of the entire graph. So absolute min means your absolutely lowest point. Your absolute max means your absolutely highest point of the graph as a whole. Relative means it's just relative to the inputs just before it and the inputs just after it. Okay? So now technically, what does that mean? F of C is an absolute minimum of F if and only if F of C is less than or equal to F of X. And that's for every X in the interval. F of C is an absolute maximum if and only if F of C is greater than or equal to all the other F of X's for every X in the interval. If F of X is continuous on the interval A to B, so now we're talking about including the endpoints. Here's your endpoint with your input A, and then there's your input with your input of B, right? So that's why they're saying we're going to include A and B this time. Then F has both a maximum and a minimum. So if your graph does not continue to the left forever, continue to the right forever, that's what these brackets mean. That's what this closed interval means. Then F has both a maximum and a minimum on the interval. It's got to end, right? It can't just keep going up to infinity forever or down to negative infinity forever. So we'll do 2 examples to show you what this looks like and how to go about doing it. We want to find a max and a min of the graph x squared minus 6x plus 2 on the interval 0 to 5. So on this very particular interval, and we're doing this without a calculator, we know that we could pick up a calculator and we could start doing all of this work as if we were in Algebra 2, but we're not in Algebra 2, we're in calculus. So our first step is to find that first derivative. So we have 2x minus 6. We're going to set that first derivative equal to 0. So 2x minus 6 equals 0. That means that x equals 3. That's our critical number, and we only have one of them, 3. Now, I accidentally drew arrows because I'm so used to drawing a number line, but we don't have a number line. We have 0 to the left, and we have 5 to the right. So it's important for us to kind of get a picture of what's happening. When I put a 0 in, I get f of 0 out, right? So what is f of 0 equal to? f of 0 is equal to, let's put a 0 in, we get a 2 out. Okay, let's look at what's happening at 3. When I put a 3 in, I get f of 3 out. So that ordered pair would be 3 and then 9 minus 18, negative 9, negative 7 is what I'm getting. Check my math. Okay, you've checked it, right? Let me write here. F of 3 equals negative 7, just to be consistent. Okay, and then we know that when we put a 5 in, we're going to get f of 5 out. And f of 5 is equal to, what is f of 5 equal to? You put a 5 in, 25 minus 30, negative 5, plus 2 is negative 3. Excellent. Okay, so here we are. We've got some values. We know what's happening with the original graph. We've got some points. If I needed to graph this, I would, but I'm not going there yet. I'm going to prove to you my answers using calculus with a graph in just a moment. I'm going to look at f prime of x. When I put a value between 0 and 3 into my derivative, if I put a 2 in, I'm going to get a negative out. That means we're decreasing from 0 to 3. And if I put a 4 in, I'm going to get a positive out, which means we're increasing from 3 to 5. So where the graph goes from decreasing to increasing, we've got a potential minimum, right? But what type of minimum is this? So let's just look at the graph real quick. 0, 2. So we're going to put a 0 in. We get a 2 out. Oh, this is going to be tough because I've got that negative 7. I can do it. I can do this. Let me erase my little picture that I was drawing there. Okay, we got this. 0, 2. Okay, put a 3 in. We get negative 7 out, something like right there. And then we put a 5 in, 4, 5, and we get a negative 3 out. Right there. So this is what's happening. So let me do this in pink. So this is our graph right there. And it's a curve because it's a parabola. So it's not a check mark, it's a curve. So what's this value? This value is going to be a high, right? That's going to be a max. This value is going to be a high. That's going to be a max. This value right here is a low. That's going to be a min. This max, this first max on the left, that's an absolute max because it's the highest point out of all 3 extrema. This max on the right now becomes a relative max. And this minimum is an absolute minimum because it's the lowest y value. It's the lowest point in your graph from the interval 0 to 5. Now, how can we do this without the graph? This point right here, where your graph is decreasing, this point before is going to be a high, right? So it's going to be a high. Then you're going to decrease from that point, and you're going to go to a low. And then when you start increasing again, you're going to go to a high. So this is a high point. This is a low point. And then following your low point, obviously, you're going to go back up to a high point. So you're looking at your 2 high points. Which one is higher, 2 or negative 3? Well, 2 is higher than negative 3. Therefore, your absolute max is equal to 2. Your absolute min, because it's the only minimum for the entire interval, so your absolute minimum is negative 7. And then you have a relative max at negative 3. Where does it occur? So now I'm going to write the ordered pairs in gray. Occurs at 0, 2, occurs at 3, -7, occurs at 5, -3. So hopefully that gives you the ability to maybe put this together and try one on your own. So we're going to try x squared minus 8x plus 10 on the interval 0 to 7. Okay, give that a try, and I will come back and provide you the answer. Okay, so you should have gotten f prime of x is equal to 2x minus 8. Setting that equal to 0, you get x equals 4. Again, I'm using arrows because it's such a habit, but that's okay because I can use my eraser. I've got 0 on the left and I've got 7 on the right. Between 0 and 4, I found that I was decreasing on my function and then increasing on the function 4 to 7. When I put a 0 into the original function, I got a 10 out. When I put a 4 into the function, I got a -6 out. And when I put a 7 into the function, I got a 3 out. Decreasing to increasing made these two on the end potential maximums. So what's higher between 10 and 3? Well, 10 is higher, so I had an absolute max of 10 occurring at 0, 10. And then I have an absolute min of -6 occurring at 4, -6. And then we have a relative max of 3 occurring at 7, 3. So you can see that our applications with our first derivative are starting to become a little bit more intense. It's more than just the skill of finding the first derivative. It's actually using that first derivative to determine increasing and decreasing portions of your graph, which lead us to finding extrema. Now, this allows us to create a graph without having to use a graphing calculator. We're also going to be talking about in the next lesson concavity, and that involves the second derivative test. So we're going to be finding the second derivatives of these functions so that we can find concavity, and concavity is a pretty neat idea. It's going to be addressed in the next lesson. If I start talking about it now, this video is just going to continue to go, and it's going to go right into our next section. I don't want to do that. So we'll see you